Algebra lesson 8-3. Now that we've been dealing with exponents and some of the situations that occur with multiplication of the exponents, today we're going to introduce the same concepts but with division. So how to deal with division. Now what's interesting is multiplication and division are very related to each other. In fact, division, I always say, is multiplication in disguise. For example, if you were dividing by a fraction, you know that you could actually multiply by its reciprocal. So there are definitely some relationships and some connections between multiplication and division. So today, we're going to talk about the division properties of exponents. We've already gone over some of the multiplication properties. I think you'll find that there are some similarities between them. First of all, we have what we call the quotient of powers. To divide powers with the same base, just subtract the exponents. Now in the past, we had dealt with a situation where we had the product of powers, and they had the same base, and we would add the exponents. So here we have an example where it's quite the opposite. It's going to be subtraction. So these are quotient, because this quotient right here means division. So that's what we're talking about. Quotient is division of the powers. Since they have the exact same base, we know that that's going to produce 3 to the 7 minus 5, which is equal to 3 to the second power. Now we could prove that another way. You could take this exact same situation. You could write 7 threes down. 1, 2, 3, 4, 5, 6, 7. And you know they're all being multiplied together. And on the bottom you could have 5 threes. 1, 2, 3, 4, 5. All being multiplied together. And whatever's on the top and the bottom of this multiplication will end up canceling out. And what you're left with is 2 threes on top. So 3 squared over 1. So this is the quotient of powers. Same base, subtract the exponents. Saves us the time of having to do that. Alright, we also have what we call the power of a quotient. You have the power of a quotient. You're dealing with a division problem that's taken to an exponent. So you find the power of the numerator, the top number, and the denominator, and then you just divide or leave as a fraction however you see fit. So here's an example of this. You could have 4/5 to the third power. Now in reality, this means 4/5 times 4/5 times 4/5. But what we're saying is, go ahead and make it 4 to the third over 5 to the third. In other words, give that 3 to both the numerator and the denominator. They each have it. Right? Now you can either leave it like this, or if you need to evaluate, 4 times 4 is 16 times 4 again is 64. And 5 times 5 is 25 times 5 again is 125. So either answer is acceptable. And you would get the same thing if you were to multiply 4 times 4 times 4 and get an answer 5 times 5 times 5. But you can distribute it. So that in itself is power of a quotient. So let's try some out here. First example has a whole bunch of 6's involved. And this is actually a combination of multiplication rules as well as division. You could take the top, since they are the same base, and add the exponents together, which would make 6 to the 8th power. Then you would have 9 on the bottom. Six to the 9th here, and 6 to the 9th here. Now there's a couple ways you could do this. You could go from this point and say, well, I've got the same base, so that's 6 to the 8 minus 9, which is going to equal 6 to the negative 1. And we already know what to do when it's a negative. You can say, well, that's the reciprocal of when it's a positive, so this would actually equal 1 over 6 to the first, which is the same as 1/6. So 1 over 6 to the first, which equals 1/6. What I tend to do is I ask myself, do I have more on top or bottom? And it's clear that I have 9 on the bottom and 8 6's on the top. So there's one more 6 on the bottom. So every one of the 6's on top would cancel out with all but one of them on the bottom. So then I know I have 1/6 on the bottom or 1/6. But you can certainly use the negative exponents as we've practiced so far. Another one. 2 over x to the 4th times x to the 2nd. Now, it's multiplication, so you can deal with this just like you want to on fractions. And another way of looking at this is 2 over x times x times x times x, being multiplied by x times x over 1. If you want to, it's okay to make one giant fraction. Now you think about everything on top compared to everything on the bottom, and one of these x's will cancel out with one of those x's, And one of these x's will cancel out with one of those x's, and you're now left with 2 on top, x squared on the bottom times 1, which just makes x squared. So your answer would be 2 over x squared. Now, again, I like to look at it and say, I have 2 x's on top and 4 on the bottom, so there are clearly 2 more x's on the bottom, so 2 over x squared would give us the same answer. But you can break it down this way if it helps you to do your math. Another thing you could do is you can go x to the 2 minus 4 equals x to the negative 2, which is really 1 over x squared. So that's another way of dealing with these exponents. And then you have 2 over 1, and when you multiply this by 2 over 1, you get 2 over x squared. In other words, the same answer. Alright? Now this one has a negative sign in it. That's okay. We're going to take this 2, we're going to give it to both the answers, numerator and denominator. So we'll end up with the opposite of 4 squared over x squared. Now you could leave it like that, or you could go ahead and say the opposite of 16 over x squared. So that's another possibility, right, where you can actually factor the 4 squared. But in this case, we're giving the 2 to both, the exponent to both. All right? What you could do is you could distribute it, or you could flip this over right now and make it 2/3 to the positive 4. So when we make the reciprocal, the exponent changes signs, and then give it to both of them. So you have 2 to the 4th, 3 to the 4th. And you could, factor that down further if you wanted to. 2 squared is 4, times another 2 is 8, times another 2 is 16. So you could say that's 16 over 81. But it's okay to leave it in the exponent form right now. Alright, now we get a little more complicated. And people make a lot of mistakes on this type of a problem. A couple suggestions that I would make. First of all, it's okay to make one giant problem. Because in reality it's multiplication, and you're going to multiply the tops and you're going to multiply the bottoms anyway. Another thing that I like to do is anytime I see a variable that doesn't have an exponent, I like to give it a 1. That way I don't lose track of what's going on. Okay? You can cross simplify just like any other situation. This 4 goes into itself once and into 12 3 times. So what I've basically done is canceled out all the numbers that are on the bottom. I still have variables, but I've canceled out all the numbers. Another thing you can do is you can cancel, if it starts to get too complicated with all the canceling out and everything that's taking, simplification that's taking place, so you can go ahead and start to put the tops together. So here's a 3, and there's a 3, and 3 times 3 is 9. And I've got x to the 3rd, x to the 2nd. Since they have the same base, we add the exponent. That makes x to the 5th. And I have y to the 1st and y to the 2nd, so that makes y to the 3rd. On the bottom, there are no more numbers because this one canceled out, but I have x to the 1st and y to the 3rd. Now what we notice is there's an exact same amount of y's on top and bottom, so these y's will cancel out. And there's how many more x's on top than there are on the bottom? This one of them will cancel out all but 4 of those. So our final, that basically took out all the x's. Our final answer is 9x to the 4th. And you could put it over 1 because you did cancel everything out, and so a 1 is left underneath. But that's really just 9x to the 4th. Alright? Another one involving quite a bit of information. We're going to take this 3, and we're going to give it to all the parts of the problem. So we will end up with 3 cubed x to the 6th, because that's power of a power, over y cubed. There's not a whole lot else you can do on this one other than the 3 cubed. So you could say that that's the same as 27x to the 6th y cubed. Because 3 cubed is 27. Okay? Now, some of the story problems that we deal with. We have this concept that t is equal to 0 is really the year of 1990. In other words, this problem is starting in 1990, and so that's the 0 year. 1 year later, a t of 1 would be 1991. A t of 5 is going to be 5 years after 1990, so it would be 1995. So here we have a problem that has 460 being multiplied by this 1.035 to the t power. This is actually exponential. We have an a value and a b value, and that's our exponent. I want to find the ratio of 1997 to 1980. So for 1997, 97 is actually going to be 7 years since 1990, right? So that means my t-value is 7. Now 1980 is a little different. 1980 is 10 years before. So 1980 is a t of negative 10. So we're going to use this equation with these different t values, and we're going to do it as a ratio. So on top will be 97, and on bottom will be 1980. So I will say y equals 460 times 1.035 to the 7th power. And down below, y equals 460 times 1.035 to the negative 10th. So in reality, the 460s can cancel out. So we know that they won't be involved in the problem. And you've got the same base with different exponents. So you should be able to say that that's really 1.035 to the 7 minus negative 10. And when you subtract a negative, you're really adding a positive. So we end up with an answer of 1.035 to the 17th power over 1. That's the relationship of 97 to 80. So the year 1997 would be 1.035 to the 17th power compared to 1. Every 1 we would have had back in 80. That's the growth that's taking place. Last example. A cube is tossed 5 times in a row. One of those rolls is 1/6. What's the probability of rolling the same number each time? 1/6 to the 5th power. That's going to make 1 to the 5th power over 6 to the 5th power. And that's quite a bit. It's going to be quite large. The top isn't, though. It's only going to be a 1. But 6 to the 5th is going to be quite a bit larger. So I'll see if I can pull up my handy little calculator here. Where are you at there? Okay. And we go 6. I don't quite have the fanciest one. 6, 6, 6. So that's 4 6s. That's 5 6s. 4, 6, 6, 5, 6. So the actual probability, the likelihood of me being able to take a die and get a 5, get a 5, get a 5, or any number I guess, the cube is tossed 5 times in a row, one roll is 1/6, probability of the same number every single time, I could do it 46,656 times and it would, probability-wise, only happen once. But not very likely to get the exact same number 5 times in a row. So again, some recaps, pretty similar. You just, when you have the same base, you subtract, and if it's a quotient, you can give it to both the numerator and the denominator.